Okay, so let's look at section 3.3. Oops, I'm not a highlighter. So in section 3.3, what we're going to do is start our differentiation rules. Okay, in section 3.1 and 3.2, we talked about what a derivative is, and we defined it using this limit definition. What we want to do today is say, well, if I use that limit definition, can I come up with some shortcuts? Okay, so for example, we're going to look at a couple of simple functions like a constant and x and say, well, what happens when I differentiate those? So suppose f of x is just a constant number c, okay? Then f prime of x, using our limit definition, is the limit as h goes to 0 of f of x plus h minus f of x all over h. Except that my function is a constant, so it doesn't matter what my input is, it's always outputting the same constant. So whether I'm inputting x or x plus h, I'm always just going to output that same constant c. And c minus c is 0. And here we have to be a little bit careful about the order that we do things in. Remember, we're talking about as h is approaching 0. So h is not actually equal to 0. 0 divided by any non-zero number is 0. So we have the limit as h goes to 0 of just the number 0, which is 0. Okay, so this gives us a derivative rule. So the derivative of a constant is 0. Or another way to write that is if f of x is equal to c, then f prime of x is equal to 0. Okay, that's our first derivative rule. Now let's step things up just slightly and look at a function x. Okay, let's suppose our color's consistent here. Suppose f of x is equal to x. Now, when we were working with limits, you know, we worked with a constant and we worked with x, and then that was as far as we needed to go. And here it's not going to be quite so clean. Our rules aren't going to be as neat, so we're going to need to look at more functions than that. Our end goal is actually going to be to look at x to any power n. Okay, so I'm just going to do one example with x, and then we'll just look at x to the nth power. So if my function f of x is just x, then the derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h. And because my function is just x, whatever my input is, that's what the output is. So if I input x plus h, the output is x plus h. Okay. So here the x's add to 0. So we have the limit as h goes to 0 of h over h, which is 1, and the limit of a constant is that constant. Okay. So the derivative of x is 1, and we could keep going with that. We could look at a couple more derivatives and look for a pattern, but I'm going to just jump straight to what we want to find. Let's look at a function that is x to the nth power. Okay, now I'm going to show this for any whole number n. The derivative rule that we're going to find will actually work for any number at all, but it's complicated to show it for fractions, and it's really complicated to show it for irrational numbers. Okay. So we're only going to do this one, and you just have to believe me that it works for the other ones, or look up the proof in the book. But I think we would have to wait a couple sections to show it for fractions anyway. Okay, so Once again, I want to start with my limit definition of the derivative. So I have f of x plus h minus f of x all over h. And here's where I'm going to pause for a moment, and I want to figure out what this looks like. Okay, so I know that f of x is x to the n. So f of x plus h is x plus h to the n, okay, which you can think of as x plus h times x plus h a bunch of times. Right. Now, depending on where you took pre-calculus and the pre-calculus you were in, you might have studied things that look like this. This is called a binomial because there's two things inside here, and we're expanding out a binomial. And in pre-calculus, you study that and you can see the formulas. And I'm not going to go into that in a huge amount of detail. One of the ways to think about it, though, when we're foiling out a bunch of these is really we're picking one of the terms from each of my multiplied factors and multiplying together. And what we do is we're going to find all of the possible combinations and add them up. So you're very familiar with the case where we just have two factors. Okay, so then we say, all right, take the x from the first one and the x from the second one. Okay, then take the x from the first one and the h from the second one. Then take the h from the first one and the x from the second one. And then take the h from the first one and the h from the second one. Okay, and that's, sometimes abbreviated as foiling it out, right? First, inner, outer, last. And when we get all the combinations. And you notice when you do that, if I take every possible combination, I could pick x every time, and I would end up with x to the n, because there's n of these factors. Or I could pick h the first time and pick x all of the rest of the times. Okay, so then I would have x to one smaller power and an h. Okay, but I could do that picking h the first time and x's for all the rest, or I could pick x the first time, then h, and then all the rest x's. Or I could pick two x's, then an h, and then all the rest x's. Right? So every single term that I have has a turn at being an h. And so the number of times that I can get this combination is exactly the number of factors that I have. There's n of them. Okay. Now, picking all x's, there's no h involved. And then we just looked at all the possible ways that I can get a single h. So then any other combination I pick will have at least an h squared in it. So I'm going to have an h squared and an x to some power and maybe an h cubed and x to some power. I'm going to have all sorts of stuff, and that's okay. I'm just going to say h squared times a bunch of stuff, and we're just going to leave it like that for now. Okay, so now let's come back to our limit. With the limit as h goes to 0, f of x plus h is x to the n plus n x to the n minus 1 times h plus h squared times a bunch of stuff. Okay, and then minus f of x. F of x is x to the n. All that's divided by h. Okay, just like we've done in the past, let's group like terms. X to the n minus x to the n add to 0. And everything left in the numerator has at least an h in it. So I'm going to go ahead and factor out an h. And what I'm left with here is nx to the n minus 1. And what I'm left with here is h times a bunch of stuff. And now that I have an h factored out of the numerator, I can cancel it with the h in the denominator. And now I can do direct substitution. And so I have nx to the n minus 1 plus 0 times a bunch of stuff. And it doesn't really matter what that stuff is because it's being multiplied by 0. So we end up with a formula. So when I take the derivative of x to some power, I get that power x to power minus 1. Right? Power comes down, and we lower the power by 1. All right. So let's look at some examples. I'm going to write down 3 functions. Let's have x to the 10th. We'll have square root of x and 1 over x squared. Okay. What I can do is use this derivative rule to find the derivatives for each one of these, right? So let's find the derivatives. Okay. For the first one, the derivative is going to be written f prime of x. And I'm just going to use my rule, right? The n is 10, so I get 10x, and then 10 minus 1 is 9, so 10x to the 9th power. And that's it. There's no writing down a crazy limit or anything. Right? We just follow the rule. Okay, for the second one, I want to do a step of work in between what I started with and using my new derivative rule, because I don't see x to a power here. But I know that I can rewrite the square root function as x to the half power. Okay, and once I do that, then I can say, okay, now I can take the derivative using my derivative rule up here. And here the n is 1/2. Now I remember I showed it to you where n is whole numbers, but trust me, it works for all real numbers. It's just harder to show. Okay, but we're still lowering the power by 1. So we'll have a negative half power. So we can write that as 1/2 x to the negative half. Sometimes we want to write it looking a little bit more neatly. So a negative exponent I can put in the denominator. So we could write this as like a 2 root x in the denominator, right? That 2 is in the denominator. The x to the half goes in the denominator, and x to the half is a square root. Okay, using that same idea on this one, I can write this x squared in the denominator as an x to the negative 2 power. And then we can apply our derivative rule. And once again, we're lowering the power by 1. So negative 2, when I subtract 1, becomes a negative 3. So again, we can write it that way, and that's fine. Or we can write this as negative 2 over x cubed, and that's fine too. Okay. Because we're going to use this rule a lot, I want to give a name to it just to reference back. This is called the power rule. Because it's powerful. No, it's because it works with powers of x. Okay. So we had a derivative rule where we looked at the derivative of a constant. Okay. And now we have a derivative rule where we look at x to a power. So those are derivatives of specific functions. Now what I want to do is take a minute to look at derivatives where we're combining functions together. So let's start with the addition rule. Okay, and what I'm going to do is I'm going to write down the end result first, and then we'll see if we can show that that's actually the case. Okay. So here's what my addition rule is. If I take the derivative of 2 functions added together, f plus g, then that's going to be the derivative of f plus the derivative of g. Okay. Now, writing down this d dx notation is useful. It means take the derivative, right? Just as a reminder, we mentioned that in the last section. Right? So it means to differentiate what's inside. Another way that we could write this, though, maybe slightly more concisely, is saying, okay, I have my f plus g, and I'm just going to put a prime out here saying take the derivative of that, and that's equal to f prime plus g prime. And what we're doing is we're just cutting down the number of symbols we're writing, and oftentimes that's okay. And if there's any potential for confusion, we just go back to being more specific about what variable we're talking about. Okay, so let me go ahead and show how this works. We're going to prove this rule because it's not too hard. Okay. What we're going to do is we're going to say, all right, I want to take the derivative of f plus g. Just to make things a little bit less confusing, we're going to say combine those together into a single function. Okay, so I'll say let s of x, right, for sum equal f of x plus g of x. Okay. Then s prime of x, that's going to be the derivative of f plus g. That's the thing we're looking for. And I'm going to go ahead and write that down using our limit definition, right? That's going to be s of x plus h minus s of x all over h. Okay. And once again, I want to figure out what I'm working with, right? So s of x plus h, since s is f of x plus g of x, that's going to be f of x plus h plus g of x plus h. Okay. So I'm just going to plug that in here. And the s of x is just f plus g. So we have the limit as h goes to 0 of f of x plus h plus g of x plus h, and then minus f of x plus g of x all over h. And then of course, I can distribute this negative. And what I'm going to do, since I have a bunch of addition here, I'm just going to rearrange the order that I write the addition in. So I'm going to write f of x plus h plus negative f of x, right, or minus f of x. And then I'm going to write plus g of x plus h, and then plus the negative g of x, right, or minus g of x. All of this is over h. But I can do something sneaky. When we add fractions with a common denominator, we combine the numerators over that same denominator. I can do that same thing backwards and say, oh, okay, I can write this over h and this over h separately. Okay. And now I know that the limit of two things added using my limit laws is just two separate limits. So I have this limit plus this limit. And if I'm paying careful attention, this limit on the left is exactly our definition for the derivative of f of x. That's f prime of x. And this limit on the right is exactly the definition for the derivative of g of x. So that's g prime of x. So we're done. We've shown now if I take the derivative of f plus g of x, I get f prime of x plus g prime of x. So the derivative of f of x plus g of x is f prime of x plus g prime of x. Okay. All right, now I'm going to make a big giant leap and say, if you're subtracting, exact same thing happens. Okay. And there's almost no difference in the proof, right? All that happens is that we've got a minus in the middle and we've got to keep track of some negatives, but otherwise it follows the exact same steps. Okay. I'm going to give you another rule, and I'm going to just skip over proving this one, just, because we don't need to see every single proof, okay? So we have our addition rule up here, and now let's look at a constant multiple rule. if I take the derivative of a function that's being multiplied by a constant, not a constant on its own. A constant on its own when we differentiate is 0. But if it's being multiplied by a function, I can just pull that constant out. And what's going to happen there is that inside the limit, I'm just going to have a constant multiplied by everything. Right? Like if I look in this, our limit definition, if I had a constant times my function minus a constant times my function, I just factor the constant outside of the limit. Right? And that's all that happens there. So constants, when we're differentiating, factor out and stay untouched. Okay, let me give you some examples now that combine these together. All right, so for each function, we want to find the derivative. So I'm gonna give a couple different functions here. Here's my first function, and here's my second function. Okay. So for the first function, what I'm going to do is I'm going to say, well, because of the addition rule, I can differentiate each one of these pieces separately. And because of the constant multiple rule, I know that the 3 is just going to hang out while I differentiate x squared, and the minus 4 hangs out while I differentiate x. So when we take a derivative here, the 3 hangs out. The derivative of x squared using the power rule is 2x. The minus 4 hangs out. The derivative of x we know is 1, and the derivative of a constant is 0. So our derivative is just going to be 6x minus 4. Okay. Easy enough. The second function, I have to be a little bit careful. We didn't talk about dividing functions yet. So I'm not going to take a derivative of a fraction. What I'm going to do is I'm going to simplify this function before I use my derivative rules. So I'm still working with g of x here. And what I'm going to do is I'm just going to write each of these over x separately. And then I can rewrite them 9 over x I can write as 9x to the negative 1 power. X over x cancel, and I'll just get 1, so this is minus 3. And then x squared over x will just leave me with an x. Now this looks like something I can differentiate because each one of these is x to a power. So now we can use our derivative rules. So here the negative 1 comes down. I have my x, and I lower the power by 1. The derivative of a constant by itself is 0. Here the 4 is a constant multiple. It hangs out, and the derivative of x is 1. Okay, what I want to emphasize with these two examples that I just did, besides the rules that we used, when you look at my work, it's very easy to see at what point I used a derivative rule, right? So like on the left here, above this orange line is the function f, and below it is the derivative f prime. Over here, I labeled it at every single step. So you can see above over here, this is the original function g. Every single one of these is the same function g. And below is that new function g prime. Okay. It's very important when you're doing your work that there's a clear distinction between when you're simplifying the function and when you're working with a derivative. You don't want to do half and half. You don't want to be simplifying part of the function in a step and differentiating a different part of the function in the same step. It gets to be very confusing to follow, both for you, for me, for anyone who's looking at it. Okay, so make sure you get in the habit of being very clear where you're taking a derivative. Okay, now let's look at multiplying functions. I'm going to start with an example to illustrate a problem that we have. Let's suppose that my function f of x is x to the 10th. And let's just suppose that because I want to, I'm going to write this as x to the 4th times x to the 6th. That seems perfectly valid, right? Okay, now I'm going to try to use my derivative rule here. Power rule on x to the 4th and on x to the 6th. So I get 4x cubed, I get 6x to the 5th. And let's just suppose derivatives work the same way that limits do, that if you're multiplying, right, you just multiply the results and you're fine, right? And what I'm going to end up with is a 24, and x to the 3rd times x to the 5th is x to the 8th. Okay. However, this was still equal to x to the 10th. So we also have that f prime of x is 10x to the 9th. And because these two are not the same, I know that something wrong happened. Okay, and it's back here, right? This is incorrect. So our derivative process doesn't work neatly over multiplication like the limit thing does. Okay, so we have to be a little bit more careful. So once again, I'm going to write down what the result is, and then we'll go through a proof of why. Okay. So this is called the product rule. And it says that if I take the derivative of two multiplied functions, f of x times g of x, I get f prime of x times the original function g of x plus the original f of x times the derivative g prime of x. Okay, so let me show you an example of that. First, I'm going to correctly work out what if I left that as x to the 4th times x to the 6th. Okay, so if I take the derivative of x to the 4th times x to the 6th, then using my product rule, we want the derivative of the first thing. So I want the derivative of x to the 4th times x to the 6th left alone plus x to the 4th left alone times the derivative of x to the 6th. Okay, so what I've done here is I've applied my rule, but I only want to do one step at a time. So I don't want to be taking derivatives while I'm writing out my derivative rule, so I use these placeholders instead. I still have to differentiate x to the 4th, and I still have to differentiate x to the 6th. Okay, so in this step, all I did was the product rule. Okay, now in the next step, what I'm going to do is the power rule. So the derivative of x to the 4th is 4x to the 3rd. And because this one is over here far away, I feel okay with doing this one in the same step also. So the derivative of x to the 6th is 6x to the 5th, right? Bring the power down and lower the power by 1. Okay. And now we do our multiplication, right? 4x to the 9th plus x to the 4th times x to the 5th is x to the 9th. Okay. And 4x to the 9th plus 6x to the 9th gives me 10x to the 9th. And remember, that's what we want. We want the derivative of x to the 10th to be 10x to the 9th. And when we just took each piece, differentiated, and multiplied up the pieces, I did not get the same result. But when I use my product rule, I do. Okay, now that's not a proof, but at least, it's an example, and it lets you know that it's going to work. Okay. Let's do another example, and then we'll look at the proof. So let's suppose my function f of x is going to be given as 3x squared minus the square root of x. Oops, not plus. The point was multiplied. Multiplied by 1 over x plus x to the fifth. Now, we don't need a product rule to figure this out. We could just FOIL this out first. Okay. But let's go ahead and use the product rule. Okay. So, using the product rule, we're going to get the derivative of the first piece. And what I'm going to do here, as I'm rewriting it, instead of writing this as the square root of x, I'm going to rewrite it as x to the half power. Okay. And then my product rule says, okay, so I have my derivative of the first times the second plus the first left alone times the derivative of the second. And here, once again, I'm going to change this 1 over x to an x to the negative 1 power. Because then it looks better for our power rule. Okay, now let's go ahead and use the power rule. So the derivative of 3x squared is 3 times 2x, or 6x. When I have x to the half, we use our power rule. I get 1/2 x to the negative half. And this next piece is left alone. This piece is left alone. And then over here, the derivative of x to the negative 1 is negative x to the negative 2. And the derivative of x to the fifth is 5x to the fourth. Okay. Now, I could get a nice, neatly organized function if I multiplied all of this stuff out. However, I didn't multiply this stuff out to begin with, probably because it was kind of a mess. And now it's more of a mess. What we're going to be doing for a large portion of this chapter is just practicing our derivative rules. And in the next chapter, we're going to look at what can we do with derivative, and we're going to be looking more at applications. We'll look at a little bit of applications in the next section, but it's mostly just to kind of get us used to the idea of what a derivative is. Okay. So because of that, we want to think of taking the derivative as practice. So in some cases, we're going to want to simplify, and in other cases, we're not going to. And I think this is a good example of where we're not going to, okay? So don't bother simplifying this any further, okay? Now, there's not really a good answer to the question, well, how do I know when I should simplify and when I should not? But if it's simple and easy, then simplify. And if it looks like it's complicated and time-consuming, then don't. Unless you have other good reasons. Like if I was going to take another derivative, I would probably want to simplify first so that I'm using simpler rules as opposed to more complicated ones. Okay, let's see if we can prove the product rule. So once again, just like with the addition rule, I want to create a new function that in this case is the product of my other two functions. So what we're going to do is we're going to start by saying let q of x, or not q, p for product equal f of x times g of x. So then my goal is going to be to find p prime of x. Okay. So let's start by writing down the definition of the derivative, right? We have the limit as h goes to 0 of p of x plus h minus p of x all over h. Okay, and my function is f of x times g of x, so if I replace x with x plus h, I'll have f of x plus h times g of x plus h. Okay, and then p of x is just f of x times g of x that I'm subtracting. The difference here, when between this and say my addition rule, all I had to do was distribute a negative and then rearrange things, and I was done. And we're not going to get off that easy over here. Okay, I have to do a little bit of a trick. I need something else to work with. So what I'm going to do is I'm going to add and subtract the same thing. And if I add something and subtract the same thing, I've really just added 0. So I haven't really changed what I have. But it's going to give me something to work with. So what I'm going to do is I'm going to add and subtract f of x plus h times g of x. And it's not really obvious at this step why I'm doing that. But then we'll see in the next step why that's so helpful. But to give you an idea, if I want to create a derivative with f of x plus h, then I want an f of x plus h minus f of x. But here the g of x parts don't match. Okay. And if I want to get like a derivative with g of x, I want g of x plus h minus g of x, but the things that are multiplied by don't match. So what I'm doing is I'm putting in a mix of plus h's and not plus h's so that I can factor a piece away and hopefully some things will match. Okay, so we'll see if that works. Okay, so I'm going to write f of x plus h times g of x plus h. And then I'm going to put in the minus one of these, right? So minus f of x plus h times g of x. Then I'll put in the plus one, plus f of x plus h times g of x. And then my last term here, minus f of x g of x. So this whole thing is still over h. And I'm going to impose like a little bit of artificial organization in here. I'm going to group these two together. And I'm going to group these two together. And if I group these two together, in the first one, I can see, well, these both have an f of x plus h in common. Okay. So I can factor out f of x plus h. And what I'm left with is g of x plus h minus g of x. Okay. And at the same time, I'm also going to break up my fraction so that I have a fraction here and another fraction over here. Okay. On the right, the thing that's common to both is a g of x. And what I have left is f of x plus h minus f of x. So it worked, adding and subtracting this term worked because now, after I'm done factoring, I can see that I have the right piece for being a derivative. I have g of x plus h minus g of x over h. I have f of x plus h minus f of x over h. And those are the right pieces I need. So if I also break up my limit into two separate limits, okay, and I need to add in another step here just to be real clear. What I'm going to do is break my limit up over multiplication also. So I'm going to take the limit as h goes to 0 of f of x plus h times the limit as h goes to 0 of g of x plus h minus g of x all over h plus the limit as h goes to 0 of g of x times the limit as h goes to 0 of f of x plus h minus f of x. All of that is over h. Okay, so then in this first piece, as h goes to 0, I'm just going to do direct substitution, okay, which works if f is continuous. But in order to do all this, f needs to be differentiable, so it's continuous. So we're just kind of skimming over some really important pieces for now. But when I do direct substitution, I get f of x. Okay, here the limit as h goes to 0 of g of x plus h minus g of x over h. That is exactly what the derivative of g is. Okay, here I'm taking a limit as h goes to 0, but there's no h's, so no worries there. And again, I have the definition of f of x, of f prime of x. Okay, now this is written in a different order than what we had before, but I can just, adding, I can change the order and that doesn't change anything. Multiplying, I can switch the order. So I could say this is the same thing as f prime of x times g of x, just writing the second term first. And then plus this guy over here, f of x times g prime of x. Okay, and our proof is done. Okay, so that's a proof that I think is, pretty accessible at the calculus level, but it's also pretty involved, right? It's not just trivial writing stuff down and then it's there in front of you. There's actually some real work about it. All right, now let's go ahead and look at the quotient rule. What happens when we divide functions? So what I'm going to do once again is write down the rule, and then we'll look at some examples. I think for this one, we'll skip the proof. It's very similar to the proof for the product rule, but because there's fractions, it's just a little bit more messy. Okay, so here's our rule. If I take the derivative of two divided functions, right, f of x over g of x, then what we get is a combination that looks like the product rule, right? F prime of x, g of x, except instead of adding, it's subtracted. Okay, except we also started with a fraction, so we're going to end with a fraction. There's a g of x squared in the denominator. Okay, and again, if we were to go through a proof, you'd see where some of these extra terms come in. You have to add and subtract things, and that's why we get these extra, a g squared instead of a g, and a minus in there. What I want to do is maybe focus on some examples. Okay. So let's say that k of x is 2x plus 3 over 9 minus x squared. Find k prime of x. All right. One of the ways that you can break this up is to label the pieces. The numerator you could label as f, and the denominator you could label as g. And in this case, that works out pretty neatly because my function isn't called f and it's not called g. Okay. So what we could do is we could say, all right, f is 2x plus 3. So then f prime, if I differentiate 2x, I get 2. If I differentiate 3, I get 0. Okay. G is 9 minus x squared. If I take g prime, the derivative of 9 is 0. The derivative of negative x squared is minus 2x. Okay. So when I write the derivative of k of x, I can start with my quotient rule, f prime g minus f g prime all over g squared. And now I just fill in the pieces that I have computed over here. So f prime is 2, g is 9 minus x squared, I have a minus here, then f is 2x plus 3, and g prime is negative 2x. All of that is divided by 9 minus x squared, squared again. Okay, and I think that this falls under the category of things that simplifying is pretty quick and easy. If I distribute a 2, I'm going to have 18 minus 2x squared. Okay, here minus a negative is plus, and when I distribute the 2x, I'm going to have plus 4x squared, and then plus 6x. The denominator is already neatly factored, so I leave that as it is. So one more step, we'll just combine some like terms. 4x squared minus 2x squared gives me 2x squared. And the other pieces don't combine with anything. Okay, so that's the quotient rule in action. And that's one way to break things up. What's going to be really important going forward is having a system for breaking up your rule into pieces. All right. Okay, I think that's it for 3.3.